This is lecture 12 for ODE, and in this lecture I'll talk about the case of a zero eigenvalue. You wouldn't expect that the phase portrait and the solutions would be so different from the other cases if you have a zero eigenvalue, but they're very different. The first thing that's different is the equilibrium solution. If you recall from our discussion previously about the equilibrium solutions for planar systems, there were two cases. If the determinant of A is not zero, then the only equilibrium solution is a trivial solution at the origin. If the determinant of A is zero, then there are infinitely many equilibrium solutions, including the trivial solution. The solutions are occupying a line, so here would be a coordinate system in your phase plane, so this is y and x. You will have this as an equilibrium solution at the origin, and you'll also have a line through there, and that's also a line of equilibrium points. So the reason that this is mentioned is because if the determinant is zero, then one of the eigenvalues is also zero. So let's look at the quadratic formula for the eigenvalues. Okay, remember the eigenvalues, the characteristic equation was so if we solve it by means of the quadratic formula, this is what we get right here. Now, if D is 0, then the result is t over 2 plus or minus t over 2. So one eigenvalue is 0, the other is the trace. Remember, t is trace and D is the determinant of the coefficient matrix A. Well, these two eigenvalues are distinct, so the solution will look just like it did for the saddle, source, and sink pattern when there were two distinct eigenvalues. And here's what the solution looks like. We've got y of t is going to be c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 t times v2. That's because there were two linearly independent solutions. y1 is e to the lambda 1 t v1, and lambda 2 is e to the lambda 2 t v2. But note that one of these eigenvalues is 0. If it's 0, then all this just becomes, of course, the constant 1. And now we have the solutions for zero eigenvalue, one zero eigenvalue, looking like this. c1 v1, just the vector, the first eigenvector, plus c2 e to the lambda 2t times v2. Also, that line of equilibrium solutions is the first eigenvector. I need to mention that. So let's look at an example. So we'll take this coefficient matrix here, minus 1, 1, 1, minus 1, and the determinant of this is 0. So D is 0, and we know that the eigenvalues, there's going to be one zero eigenvalue. Note that the trace is minus 2, and previously, if you can recall, lambda 1 was 0 and lambda 2 was the trace. So here are the two eigenvalues, so we have them immediately, 0 and a minus 2. So we'll go through the procedure for finding an eigenvalue, just like we did for the source, sink, and saddle case. So we have the first eigenvalue, looking for the first eigenvector, substitution of A minus, and then this is 0, of course, so it's just the A matrix, times vx1, vy1, vector of those, equaling 0. And the easiest eigenvector you can think of for this case, of course you can see what it is, you have to have minus vx1 plus vy1 equals 0. Obviously, if they're equal, that will work. So let's set them both equal to 1. So here's v1. It's just, that's the vector. Okay, for the second one, we have a non-zero value for the eigenvalue. Work through the same equation, substituting lambda 2, looking for the components of vector v2, and this is what it is. So writing this in component form, you have vx2 plus vy2 equals 0. Obviously, if they're equal and opposite, that equation would be satisfied, And so here's the choice for V2. Now we have our two eigenvectors and we have the two eigenvalues, one of them being 0. And here's the solution. We have y equals c1 and just times v1 because e to the 0 is 1, so that falls off. And then we have c2 e to the negative sign here, minus 2t times v2. So here's v1, here's the v2, and now let's look at what happens to these solutions in time. Okay, we'll take the limit of this equation. No, I'll never learn that, will I? We'll take the limit of y of t as t goes to infinity. Okay, c1, v1 is not time dependent, so that stays. But the limit of this other term goes to 0. So these equations are approaching that first eigenvector. And here's what the pattern looks like. So here was the first eigenvector right here, v1. Okay, so I'll write this down again, sorry about that. Here is that eigenvector v1. It's also the line of equilibrium solutions. Every point on this line is an equilibrium solution. Okay, that means if you put the points on this line into your original differential equations, original system, the result would be, it's a vector, of course. Okay, and here are the solutions. They're approaching these because this is a sink. If your eigenvalue was positive, they would be moving away, but the approach would be in backward time. If you recall that phase determinant plane, let me erase this for a second. Okay, so we had a phase determinant plane. Okay. So here was the trace, and here was the determinant. Right. Then there was a parabola that came through like this, and that was, whoop, it should hit the origin, sorry about that. This was t squared equals 4d, and in here were the centers and the spirals. Okay, and right along this line, okay, it's a single tangent patterns. Under here was sources and saddles. These 0 eigenvalues are along here because that's the line in which d is 0. So this is where your single eigenvalue patterns would be in the TD plane. The one right here would have 2 0 eigenvalues, and it consists of lines, straight parallel lines. Otherwise it's a line with the solutions approaching it, approaching the eigenvector v1, the eigenvector associated with the 0 eigenvalue.